Alright, welcome back. This is going to be a video on graphing exponential functions. Just going to talk about the basics of an exponential function real quick. First and foremost, an exponential function is considered an exponential function because the variable is in the exponent spot. So you'll notice that x is an exponent rather than having a number being an exponent. So I'm going to just make a quick table. So x, y, right? So I'm going to go like -2, -1, 0, 1, and 2. It's like everybody's favorite. And so when you're looking at this graph, like if you put -2 as the exponent, 2 to the -2, what do negative exponents make you do? They make you take the reciprocal, so that'd be 1/4. So 2 squared is 4. 2 to the -2 would be 1/4. So this would be 1/2. This would be 0, or 2 to the 0 power would be 1, excuse me, right? So when you put 0 as the exponent, remember, it always makes everything just 1, not 0. And then 2 to the first would be 2, good grief, 2. And then 2 to the second would be 4, all right? So I'm going to plot those points. Oops, plot that guy in the wrong spot. Here we go. If you did 3, it'd be at 8, and so forth. 4 would be at 16. So -1 was at 1/2, 1/4. And I'm not sure if you know this, but it would never equal 0. The y value will never equal 0. So we'll get what's called a horizontal asymptote with graphing exponential functions at y equals 0. And we'll never cross the horizontal asymptote in these types of functions. And so here's this green graph. This would be considered exponential growth, and we'll talk more about that in our video. The next one, I'll just make another table real quick. -2, -1, 0, 1, and 2. And if you plug in -2, once again, it's going to make you take the reciprocal. And so 1/2 to the second power would be 1/4, but then you flip it, so it'd be 4. This guy's going to be 2. This is going to be 1. 1/2 to the 0 power would be 1. 1/2 to the first would be 1/2. 1/2 to the second would be 1/4. And so here we go. Got this guy at 0, 1 again. -1, 2. -2, 4. If you plotted -3, it would be at 8. And 1's at 1/2. And then 1/4. And so you can take a look at this guy. This exponential function would go down from left to right. And so that would be considered exponential decay. If you could envision with me, there's probably another 2 graphs that you could see happening. If we were to take the green graph and reflect it over the x-axis, it would look something like this, right? And if we were to take the red graph and we were to reflect it over the x-axis, it would look something like that. So for exponential functions, there's probably 4 different directions that you could get them to look, and that would be it. So to make the reflection over the x-axis happen, just remember that you would need a negative, right? This would be multiplied by a negative. So to kind of lead into that, let's just talk about critical parts of an exponential function. So this would be considered the general form of an exponential function. You have a, which is the coefficient, and this guy is going to be just a number, a scalar. It doesn't have too much of an effect on the graph in the sense that it's not going to change like the look of the graph, but it will cause a reflection. So if a is less than 0, I guess it would change the direction, but it's not going to change the curvature or anything like that. It may make it steeper or less steep, but it doesn't like make it look different. So anyway, a is less than 0, then that would be a reflection over the x-axis. Okay, and then it's your standard vertical shrinks and vertical stretches, right? If that kind of stuff is asked of you, hopefully you know what is being talked about. The base is much more critical. So this is considered the base, right? And this is what really changes the graph a lot. So sometimes the base will be greater than 1. That's the first scenario. Sometimes the base will be in between 0 and 1. But two things that the base won't be: the base won't be 1 or negative. Right? If the base is 1, then the graph is just like a flat line and it doesn't really do anything. But if the base is negative, then the graph looks super weird. And if you want to see what that would look like, you can get crazy and put it into your calculator and do like y equals parentheses -2 close parentheses and then raised to the x power. And then you start seeing this thing just jump up and down, and it's not continuous. So we're looking for a continuous smooth curve. And so since we want a continuous smooth curve, you have to have a base that's either greater than 1 or in between 0 and 1. But it can't be 1 and it can't be negative. Alright? Then the last thing is h and k. Right? H is your left and right. Shift. It doesn't change the look of the graph necessarily either. The one thing I will say is if there's a negative in front of the x, then that would flip over the y-axis. And then the last one, k, right, it's your up and down shift. Alright? But the second thing about k is that it is also the horizontal asymptote. Right, if we go back to our graphs that we graphed, if you're taking notes or you're thinking about this with me, if we go back to this graph, every basic exponential function is going to have a horizontal asymptote at y equals 0. However, if it's shifted up or down, that function will now have a horizontal asymptote at the shift. And so this will also be the horizontal asymptote. So you can think of this as the horizontal asymptote is always at y equals k. So if there's no shift, then it's at y equals 0. But if there's a shift, then it's going to be at y equals k. Alright? Whoops. So let's take a look at graphing one of these guys just real quick. And then we'll talk about exponential growth and decay. So let's take a look. Horizontal asymptote. We do have a vertical shift, right? So it's at up 4. So we'd say our horizontal asymptote is at y equals 4. So I'm going to draw in a dotted line at y equals 4, and I know my graph's not going to cross there. We have a shift left 1, but that's kind of hard to see. And then also we have a negative in front, and so we know that it's going to be flipped over the x-axis, so the graph will be below the horizontal asymptote. Alright, I'm going to just make a table of points if that's alright with you. Probably the easiest thing to do. So let's just pick like negative 2, negative 1, 0, 1, 2. Sometimes the numbers can get kind of big and I may not even plot them, but we'll see how it goes. So I'm just going to plug them in to find y values. So y is going to equal negative and then 3 to the negative 2 plus 1 plus 4. So what's that? We got like negative 3 to the negative 1. So 3 to the negative first power is 1/3. So we have negative 1/3, right, plus 4. So we just say 3 and 2/3. Is that alright? I'm going to go real crazy and do mixed numbers for you. If I plug in negative 1, that would be 0. Anything to the 0 power is 1, but then apply the negative. So it'll be negative 1. And then plus 4 is 3. And then if I plug in 0, that's going to be 3 to the first power, which is 3. Apply the negative, and then plus 4, so it's 1. Plug in 1, that's going to be 9, negative, and then negative 5. If I do 2, that's going to be negative 27, plus 4 is negative 23. I'm probably not going to plot that last point, so here we go. Negative 2, and then it's going to be 3 and 2/3, so about right here. Negative 1 is at 3. 0 is at 1. 1 is at -5. 2 is at -23, and I'm not going to plot that. Alright, and there is our graph. Okay, so let's talk about domain and range of these guys. The domain is how the graph moves left and right, and the beauty of exponential functions is that their domain is all real numbers. There's nothing you can't plug in for x that would break some math rule for exponential functions, so you just plug in the domain and you should be good, or the domain should be all real numbers. You can plug in anything you want. You can find a point for it, a y value. The range, though, you do have to think about the graph a little bit. So we have our asymptote here at y equals 4, and the graph is below it, and so we're going to say that it goes from -infinity, the y values, right, goes down forever, but it goes up to 4, but it doesn't equal it, and so we would say up to 4 with parentheses. Remember, you always go least to greatest with interval notation. You could also say this is like y, or you could say this is like y is less than or equal to, or excuse me, not equal to, silly me. You can go y is less than 4. End behavior is just talking about what this graph is doing at its end. So remember, end behavior is written this way. F of x goes to something as x goes to -infinity, and f of x goes to something as x goes to positive infinity. And so all you're saying is, what's the graph doing to the left? Like, as the x's become more negative, what's the graph doing? And in our graph, it's approaching the horizontal asymptote. You can see that here. This is what the graph is doing as x goes to -infinity. It is getting closer and closer to 4 as it moves to the left. So we would say it's getting close to 4. The y values are getting closer and closer to 4. And then as it goes to the right, we see that over here, as it moves to the right, this is what it's doing as x goes to infinity. The graph's going down, so the y values are just becoming more negative. And so that would be how we would describe the end behavior of this function. Okay? The last thing I want to talk about is just exponential growth versus exponential decay. And this is really getting into like modeling. You see exponential growth with modeling, and by that I mean a fancy word for word problems, right, where we're modeling a scenario like the population is growing exponentially, or the medicine in a bloodstream is decaying exponentially, or we talk about radioactive decay, or talk about interest, compound interest growing. So we see this exponential growth versus exponential decay a lot in word problems. So to know the scenarios of when it's happening, this is exponential growth. We graphed it earlier. Whoops. So this is exponential growth, this guy right here. And the reason it's exponential growth is because a equals 1. You can't see it. There's a 1 right here. Being multiplied by 2 to the x, and then the base is 2. So exponential growth will occur when a is positive and when b is greater than 1. This graph, exponential growth, always looks like this. It always grows to the right, just like that. Okay? That is the only graph that I would consider to be exponential growth. That's the kind of graph that we use when like populations and compound interest and things like that, when we're making those problems. That would be it. The second one is exponential decay. Now, why is this exponential decay? Well, we got to think the negative exponent does things to this whole thing. So another way to write this would be y equals 1/2 to the x. And so we graphed that earlier, and we saw that the graph looked like this. Right? The graph looked like this guy. And as we move from left to right, the graph is going down. And so in this case, a is 1, right? There's still a 1 being multiplied by that 1/2. And the base is not 2, the base is 1/2 actually, because we apply the negative exponent. And so exponential decay will always occur when a is greater than 0 and when the base is in between 0 and 1. Okay, that's it. So a couple things. One, you don't always get exponential growth and decay. These are not like the only exponential functions that there are, because if a is negative, then it just reflects it over the x-axis, but we wouldn't consider it exponential growth or decay. All right, so we're going to play a game. Let's play a game. It's just growth or decay, or I guess you could say neither of the two. So if you want to play the game on your own, hit pause right now. Decide if these are exponential growth or decay. I'll give you a second. 1, 2, 3. All right, cool. Hopefully you hit pause at some point and you decided whether these were exponential growth or decay. Here are the answers. Ready? If I apply the negative, this is going to become y equals 5 to the 2x. Therefore, this is growth because a is greater than 0 and b is greater than 1. All right, next one. No negatives in the exponent, so this is just straight up it. So a is greater than 0 and b is greater than 1. So this is also growth. Wow. Let's see if the trend continues. All right, a is negative, so now it's neither. Trick question. It is neither growth or decay. Boom. All right, friends, that's it. Hopefully you enjoyed the video. Got a good lesson on exponential functions. You're welcome. Have a great day. Talk to you later.